Chapter 3, Elements and Compounds. Here we have a picture of a golden Buddha statue. A lot of statues that still exist from the ancient world are made out of gold. And that's not because everything was made out of gold back in those days, but it's because gold does not decompose. And so of all the things that were constructed in the ancient world, things made out of gold have the best chance of still surviving today. And so that is why a lot of ancient artifacts are gold, because gold is inert. You come back 5,000 years later and a gold statue looks almost exactly as it did when it was first made. Gold is extremely inert. Historically, all people have always liked gold. Gold has been a monetary unit in many different cultures, making gold coins. Especially, even in the United States, our original money was based off of gold. And so gold, copper, and silver have a long history in coins. And so when America was founded, pennies and half pennies were made out of copper. Dimes and half dimes were made out, and quarters and dollars were made out of silver. And then quarter eagles, double eagles, eagles were made out of gold. And so the penny was a unit based off of copper. The dime and dollar were units based off of silver. And then the eagle was a unit based off of gold. So if you see really old American coins, you'll notice we had half dimes before they just made nickels instead for 5 cents. Because it originally started as a silver unit. We believe psychologically people like gold because it glitters yellow. The most important resource for people is water. People would have always been looking for water. And when the sun shines off of a body of water, it glistens in a golden color. And so we think, theoretically, that is why people are very drawn to gold. But all cultures across the world have always been drawn to gold and use gold for these purposes. So this chapter is about elements. Elements are any fundamental substance that cannot be broken down by chemical means. Now, if you look ahead in chapter 18, we don't get to it in this class, but there's nuclear chemistry in chapter 18. You can break down an element. Radioactivity is a form of an element breaking down into other elements. But that's not a chemical process. That's a nuclear process. So in chemistry, the fundamental basic building blocks are elements. You cannot break an element down doing chemistry. Most elements on Earth are found naturally. Some are synthesized by man. 92 is uranium, and that is the biggest element found naturally. 93 through 118 are only synthesized artificially in labs. The least amount of an element you can have is an atom. And atoms are made up of subatomic particles. This class does not go deep into subatomic particles. Electrons, we still believe, are fundamental particles, and then there's neutrons and protons. Neutrons and protons themselves are made out of quarks, but we don't worry about that in this class. For this class, we only go down to the proton, neutron, and electron level. Anything further than that is no longer chemistry. That is particle physics. And currently, there's 118 elements known. 88 of these occur naturally on Earth. The other 30 of them have been synthesized artificially in labs with bombarders. At room temperature, only 2 are liquids, bromine and mercury. If you look at the periodic table, bromine is a liquid due to van der Waals forces, which we will cover in later chapters. But to get you a head start on that, basically, imagine an atom. Let's say I have my bromine. And bromine is a diatomic element. 2 are always found together. The bigger an atom gets, the more protons it has, and also the more electrons. Now these electrons are just whirling around randomly. So let's imagine that just randomly more than 50% of the electrons went to this side, just instantaneously. That would make this side negatively charged, just for a moment, because the electrons are going to move. But for that instantaneous moment, we'd have a negative charge here. That would pull on this bromine, and therefore, because you'd have a positive on this side of the bromine. If you have a negative on one side, the electrons got pulled over here, there's a positive on the side that doesn't have many electrons, and that would affect the atom next to it. And so that's a basic synopsis of van der Waals. It's the instantaneous, temporary, always changing negatives and positives that form through the completely random chaotic motion of electrons. And the bigger an atom gets, the more of those forces they are. So if we look at group 7, the halogens, fluorine is a gas, chlorine is a heavier gas, bromine is a liquid, iodine is a solid. And so we go from gas to liquid to solid just because we're getting more and more and more van der Waals forces. To understand why mercury is a liquid, that both takes more physics knowledge and more chemistry knowledge. But to summarize it, mercury is at the very end of the D block. So if you look at it on a periodic table, it's in the middle chunk of transition metals, but it's at the very end. So it has a completely full electron shell, and that makes it more stable. But also, if you look closely at the periodic table, you'll notice that the inner transition metals, there's 2 rows of your periodic table that are at the very bottom. They actually should fit in those rows. There'll be a gap. And basically mercury is the first element that is has this stable conformation, and also the nucleus has gotten so huge that the forces on the electrons are big enough now that special relativity comes into play. And so in physics, there's theories about how when something's moving closer to the speed of light, time slows down and things change. And it's actually those effects which cause the mercury atoms to be incapable of making good metallic bonds to other mercury atoms, and it ends up being a liquid. If you look right below mercury at atom 115, that one actually, hypothetically, we believe that one is a gas. Only 3 atoms have ever been made, but we think if we had a sizable sample to actually see it, then we think that one would actually be a gas. Or sorry, 112. 112 is directly below mercury. Again, only 3 atoms have ever been made, so no one really knows. And then that's true for most of those really heavy ones. The further you get past 92, the less and less stable they are. And in general, only a few atoms have ever been made just for the sake of proving that they could be made. At room temperature, 11 are gases. So we had 2 liquids at room temperature and 11 gases. And basically you have hydrogen, nitrogen, oxygen, fluorine, chlorine, and then the 6 noble gases: helium, neon, argon, krypton, xenon, and radon. So of these 11 gases, 6 of them are the noble gases. And then you have hydrogen, nitrogen, oxygen, fluorine, and chlorine. Of the 118 elements, 2 are liquids at room temperature, 11 are gases at room temperature, which leaves us, we take 118, we minus 2, we have 116, we take away another 11, and we have 105. So we have 105 elements which are solids at room temperature. So the easiest way to know which ones are which is just learn the ones that are liquids and gases, and then all the other ones are solids. 10 elements make up 99% of the mass of Earth's crust, seawater, and atmosphere. Oxygen makes up a whopping 49.2% of Earth. Silicon makes up 25.7% of Earth. Because silicates, like sand, are just silicon and oxygen, and because that makes up 3/4 of Earth, it's no surprise that you find sand everywhere. We go to the Caribbean, there's sand. East Coast, sand. West Coast, there's sand. You go to South America, there's sand. Australia, there's sand. Pacific Islands, there's sand. Asia, there's sand. There's sand everywhere. There's quartz everywhere. Because these are the basic building blocks of Earth. And also, silicon really likes to bind to oxygen. And so because they're both found in large amounts and they both like to chemically react with each other, quartzes and quartzites are extremely common in geology. Now we add in aluminum, and now we have clay. Clays are aluminosilicates: silicon, oxygen, and aluminum. And notice that aluminum is the 3rd most common element on Earth. The history of aluminum is interesting because it used to be extremely rare because it was so hard to purify. It takes a lot of electricity, which wasn't very common before electricity was developed. And so aluminum used to be a precious metal. It was treated like platinum. Forks and spoons were made out of aluminum for like emperors to use. The cap of the Washington Monument was made out of aluminum. These days it's not appreciated, but back then that was a huge thing. That would be like gold capping a monument, because that was the most precious, most awesome, most space age metal of its time period. And it's also the only metal that has changed from precious metal to common. Because once electricity was invented and they realized that aluminum was actually really common and found everywhere there's clay, which is everywhere in the world, aluminum's value dropped significantly. And now, because it was so common, we don't use it for engagement rings and special things to host emperors. We use it to wrap sandwiches. And so aluminum is the only metal that ever changed from precious metal to common industrial metal, because it's very common. They just didn't know how to purify it. And so it used to be very rare in its pure form, but these days it's extremely common. Iron, 4.7%. Iron is useful because it's very strong and it's very common. In one star, you can make up to iron, because basically when the sun's reacting, hydrogen's being fused into helium. And that works until you run out of hydrogen. Then the helium starts getting fused into heavier elements, and those get fused into heavier elements, and those get fused into heavier elements, and you can finally make iron. To get elements heavier than iron, that occurs when two stars crash into each other. So that's a much more rare event. So elements heavier than iron are much, much, much more rare in the universe. And then we have calcium, sodium, potassium, magnesium. These are the ions that the human body uses in bulk. You use sodium and potassium to run your nervous system and run your muscles. Calcium is in your bones. It's also used in muscle contractions. It's used anytime you have exocytosis and you need calcium ions so that the T snares and the V snares bind, so you can emit a neurotransmitter into the neurotransmitted cleft, or the synaptic cleft of the nervous system. So calcium's used a lot in the body. Sodium's used a lot in the body. Potassium's used a lot in the body. Magnesium is used a lot in the body, which is important to know, because when an American has a mineral deficiency, it's typically magnesium. The only good source of natural magnesium is chlorophyll, which comes from dark green vegetables, which is not eaten enough in the average American diet. And so magnesium is useful because it's used to counter the charge on ATP. ATPs have a -4 charge, and a lot of enzymes use 2 magnesium plus 2s to stabilize that. And so a lot of enzymes in the body that use ATP, which is very many of them, need the magnesium in order to properly work. And so magnesium is also necessary in large amounts. And so it's no surprise that the human body uses these elements, because these elements are very, very common on Earth. And so biology uses the chemical tools that are at its disposal. Then we look over here, we have hydrogen, titanium, chlorine, phosphorus, manganese, carbon, sulfur, barium, nitrogen, fluorine, and then every other element only makes up less than 0.5% of Earth in total. Oxygen accounts for about 20% of the atmosphere. And again, it's found in all the rocks. It's found in sand, it's found in soil, and water. Water is H2O. And so oxygen, again, is everywhere. The human body has a very similar elemental use, except we use carbon. We use carbon instead of silicon. And carbon is useful because it can bind to itself hundreds of times and still be stable. And silicon cannot. After about 10 silicon-silicon bonds, it gets unstable and breaks down. And that's why life is carbon-based, because only carbon can make the huge molecules necessary for the complicated functions of living entities. And so you need carbon. And so carbon has taken the place of silicon here. Science fiction shows like to look for silicon-based life, but honestly it's probably not possible, because silicon itself is not able to bind to itself enough times to make the complicated molecules that carbon can. And so carbon is a much better molecule for life. And that is the end of part 1.